Greetings, traveler. I am the calculus cleric, and today we'll be working on Maclaurin series. The problem is to find the Maclaurin series and find the interval on which the expansion is valid for f of x is equal to e to the x minus 2. Now, before we go into any official steps, the first thing I would like to do is separate this out into its base components. That'll make it easier for us in the long term. Separating out into individual components, you get e to the x multiplied by e to the negative 2, because when you multiply two bases that are identical, then you can simply just add the exponents together, just like that. And what we're going to do now is simplify it even more. What we're going to do is factor this out and leave it off to the side, because it's a constant, which means that it won't impact the results of the sum if we just multiply it in later, because you can factor constants in and out of sums. So now we'll focus on e to the x. We'll generate a sum for that first, because it even has a variable in it as well. So we can't treat this as a constant because of the presence of that variable. So to create a sum, or the Taylor series actually, we'll have to find the Taylor polynomial first. So our f of x, let's just call that e of x right now. I don't want to deal with the constant 1 over e squared. It would work if you were to do it inside and consider it part of the f of x that we're doing. Because it's Maclaurin, it's given to us that this x value is 0 because of the word Maclaurin. Now if I take the derivative of that, the derivative of e to the x is also e to the x, and you see where this is going. Now at this point I'll stop because I don't need to go any further, because you may have noticed that this will generate an infinite loop, because it will continuously, if I keep taking derivatives of e to the x, it'll just be e to the x, e to the x, e to the x, which is just the same thing over and over and over again. So I'll always be a coefficient of 1. Excellent. So let's turn that into a Taylor polynomial. Let's take that out to the degree of 4, just so we can take a look at the other variable degrees and the factorials that will arise from this. So our first term is just 1 by itself. The next one is coefficient of 1, and then x minus 0 to the 1th, which is just x, all over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial. Now we're asked to generate a series, which is a sum, so we'll get our sigma here. And then we need to find what goes inside here. I'm going to call this f of n. And basically what the n is just the term. So one term, this is another term. And they go in numerical order of increasing degrees. This will be our 0th term. This will be our first term. And it'll be our second, and so on and so forth. So what we need to do is to find a pattern between each of these different terms. So when I plug in a different n value for where it is, it'll generate this term. The first thing I like to focus on is these variables. They're often the easiest thing to solve. And looking at this, we'll see that as our n goes up by 1, these also go up by 1. So when this is 0, it's 0. When n is 1, this is 1. And when n is 2, it's 2. When n is 3, it's 3. So on and so forth. And so we can just call that x to the n. Whenever n is some number, x will be that power of n. So x to the n. And now we'll focus on the bottom half, which is the factorial. So here you'll notice that it's 1 factorial for first term, 2 factorial for second term, 3 factorial for third term, 4th factorial for fourth term. Hey, wait. It's just like the first one, where we have n going up by 1 each time. So that will be a nice n factorial on the bottom. And when this is 1, which is the 0 term, it'll be 0 factorial, which is equal to 1. So that all works out. And we can plug our f of n back into this sigma. And then set that equal to infinity, because that's what the Maclaurin series is. We're taking this out to infinity. And then we'll start at 0, because we're calling this our 0th term. And it makes it so much easier when we do a rule like that, so we don't have to worry about the 1 if it was not, say, a 0th term. But now we can't forget this guy. We said we'd leave him out and we add him back in later. Basically, what I meant was we're keeping him outside like that. We're factoring him out of the f of x, but we can always add him back in. It makes no difference to the resultant sum. And adding him back in, this will make it easier when we're solving for our interval. We get this. And that is our Maclaurin series, and on to the second step, which is finding the interval. So now we have to find the interval of this Maclaurin series that we just found, and to do that, I would like to use the ratio test, because I don't see any roots and I don't see any other test that would be more beneficial. So the rule for the ratio test is as follows. And the reason why we're using the ratio test is because the ratio test is a good indication on where something converges or not. And that is the equation for the ratio test. So first we have to figure out what a of n and what a of n plus 1 is. A of n is easy. It was equal to our f of n that we found earlier on, which is simply just this part of the series that we generated. And so we can just write that down. It's a freebie. And now a of n plus 1, where we just simply replace all these n's in here with an n plus 1. Be careful that we distribute properly, but that shouldn't be a problem here, seeing as there's no coefficients. Okay, now we can just apply these two and put them back into this equation above. Looks like we got a lot of terms left. So when we come across problems like these where we want to cancel everything so it becomes much more simpler to take the limit of infinity, I don't want to take the limit of infinity with that factorial up there and on the bottom. So we can break this side apart into its component terms, because it got plus 1. And just like above, we can break that apart. We'll do the same thing here. And factorials, we can decompose them in the same way. So when we have n plus 1 factorial, it's really equal to n plus 1 multiplied by n factorial. It's the same thing. Similar to how I take 5 factorial, and I just change that to 5 multiplied by 4 factorial, because 5 factorial is 5 by 4 by 3 by 2 by 1, and 4 factorial is 4 by 3 by 2 by 1. So if you substitute those into each other, they'll be the same thing. Nice. Now it'll be really easy to go and factor a bunch of stuff out. I can see a lot of things to cancel out, and let's do that. So our limit becomes a lot easier to solve. And we're left with this. And when we solve the limit, when we plug the limit in, it'll get an infinity on the bottom and an x on the top, where x is just some number. So therefore, this will equal 0. When the ratio test is 0, the answer works for all x values. Therefore, by the ratio test, the series that we found above converges for all x, which is another way of saying all x values that are real.